Ever watch a figure skater launch into a triple axel and think, how do they time that perfectly? Well, scientists are teaching computers to figure it out, and the results are mind-blowing. Today, we're breaking down how AI is revolutionizing the way we analyze figure skating, one jump at a time. Let's start with a big challenge. Why is this even hard? Figure skating jumps aren't just fast, they're 3D puzzles. A skater's body twists, spins, and glides in ways that defy simple 2D tracking. Traditional methods rely on human judges or basic motion sensors, but those struggle with camera angles, lighting, or the sheer speed of a triple rotation. It's like trying to track a spinning top with a blurry camera. Enter VIFSS, a two-step AI system designed specifically for skating. Think of it as training a robot to recognize a jump, no matter how the camera is angled. First, the AI learns to spot movements from any perspective, using a technique called contrastive learning. It's like showing a child thousands of photos of a cat, from every angle, so they can identify a cat even if it's sideways or upside down. This makes the AI view invariant. It doesn't get confused by camera shifts. But here's the real twist. VIFSS doesn't stop there. The second step is fine-tuning, training the model on a groundbreaking dataset called VIFSS Jump 3D. This isn't just any data. It's the first public 3D pose dataset for figure skating, captured using markerless motion capture. Imagine a library of elite-level jumps, with every joint tracked in real time, from the exact moment a skater pushes off to the split-second landing. What makes VIFSS Jump 3D special? It's not just about raw data, it's about details. Researchers annotated every phase of a jump, the entry, the rotation, the landing. This fine-grained approach lets the AI understand the procedure of each move, not just the end result. For example, it can tell the difference between a 3-lutz and a 3-toe loop based on subtle shifts in body position and rotation. So how does this work in practice? The AI first uses contrastive learning to build a pose dictionary that ignores camera angles. Then it's trained on VIFSS Jump 3D to recognize the unique language of figure skating. The result? A model that detects jumps with over 92% accuracy, even in messy, real-world videos. No more guesswork, just precise data-driven analysis. But here's the kicker. VIFSS isn't just accurate, it's adaptable. Researchers tested it on two types of data: set-level, overall routine, and element-level, tiny details like arm positions or foot placement. The results? VIFSS smashed the competition. At 94.68% accuracy on set-level tasks, it even outperformed 3D pose models. But the real win? Over 92% accuracy on element-level analysis, catching the tiniest nuances, like the split-second shift in a skater's posture during a triple axel. Here's where it gets even cooler. The team did an ablation study, a fancy way of testing each part of the system. They found that pre-training with view-invariant data was a total game-changer. Even with just 1% of the usual training data, VIFSS still nailed 70% of set-level tasks. That's huge for real-world use, where labeled data is often scarce. Why does this matter? Imagine a coach getting real-time feedback on a skater's technique, or an automated system grading routines with pinpoint accuracy. VIFSS isn't just about skating, it's a framework designed to adapt to any sport. The researchers tested it on skating, but the same tech could analyze basketball dunks, soccer kicks, or even gymnastics flips. The secret sauce? A custom dataset called VIFSS Jump 3D, built specifically for skating movements. But the real innovation is its ability to learn general motion patterns, making it flexible for other sports. It's like a universal translator for athletic movements. And here's the best part, the code and data are open source. Researchers worldwide can build on this work, pushing the boundaries of what AI can do in sports and beyond. So what's next? The team wants to test VIFSS in chaotic real-world scenarios, like a soccer match with 22 players or a skate park. The future of motion analysis isn't just about seeing movement, it's about understanding it. Thanks for watching and stay curious.